Welcome to Mr. Brown's Basement, a channel devoted to sharing the craft of repairing, restoring, and modifying vintage electronic gear, and other random stuff. Recently, Mrs. Brown plugged an appliance into a GFCI, that is, a ground fault circuit interrupter receptacle in her bathroom. There was a spark and a loud pop, and Mr. Brown was called to examine and replace the receptacle. I thought I'd use the opportunity to rip it apart to look inside. I'd never seen the inside of one before, and also explain how these deceptively simple devices protect people and property by detecting ground fault conditions. A GFCI acts like a circuit breaker, cutting off power to a load. However, unlike the circuit breakers found in your house's load center that only act when an overcurrent situation exists, a GFCI detects a fault in the ground circuit, which is there to protect you against accidental electrical shock. GFCIs are engineered to do this without even connecting to the ground conductor. You can see where the arc occurred. It was hot enough to mildly char the surface of the plastic. Let's take apart Mrs. Brown's GFCI. 4 screws hold the sandwich together, which includes the front plate, the back plate, and the middle section with the electronics. This GFCI was made by Leviton probably about 20 years ago and was designed around the Texas Instruments LM1851 GFCI integrated circuit. The other circuit components are through-hole devices. The actual circuit is almost exactly the typical application circuit provided by the IC manufacturer. Newer GFCIs use other, more modern ICs and surface mount devices. The middle section contains a control board at the back and a triple pole switch at the front. The switch is activated by a solenoid, that is, an electromagnet, or by the test switch. When it's activated, the switch opens both the live and neutral connections from the line to the receptacle. The third pole resets the control circuit. To restore power and close the switch, you press the reset button. Here is the typical application circuit for the LM1851. Inside the GFCI, there is a differential transformer labeled sense coil. Under normal conditions, when there is something plugged in and operating, there's a current flowing on the live conductor and the neutral conductor. The currents are equal, but in opposite directions. Live and neutral pass through the differential transformer, but the magnetic fields created by live and neutral cancel each other out because they're equal and in opposite directions. Suppose, however, your grounded hairdryer drops into the sink, and current flowing into the hairdryer on the live conductor is now flowing out, both on the neutral conductor and the ground conductor. If that happens, more current is flowing on the live conductor than on the neutral conductor. Inside the differential transformer, the currents on the live and neutral are no longer equal and opposite. The difference between them is detected by a comparator, which amplifies the difference and sends a signal to a silicon-controlled rectifier to activate the solenoid, killing the power to the whole circuit and to the hairdryer, and possibly saving your life if you happen to be touching it at the time. This will happen with only a few milliamps of difference between live and neutral. There is a time delay between when the fault condition is detected and when the switch is opened. This reduces the chance that the switch is falsely tripped, but can also permit the fault condition to go on longer, especially if there isn't much current flowing on the ground. The time delay and sensitivity values are set by external components and can be customized for different applications. Unfortunately, it doesn't take much current to kill you. As little as 7 milliamps across the heart for 3 seconds can kill. GFCIs have a second function, that is to detect a short between ground and neutral. As mentioned before, during normal conditions, current on the live and neutral are exactly the same. That's because the resistance of the live and neutral conductors from the load center are exactly equal. But imagine if the ground and neutral conductors were shorted together downstream of the GFCI. This would defeat the purpose of the ground conductor. Since the neutral and ground are connected together in the load center, shorting them together downstream puts both the ground conductor and the neutral conductor in parallel, splitting the current between neutral and ground. To detect this, there is a second transformer which injects a high-frequency signal using the primary winding and a capacitor as a resonant circuit, excited by the 120 Hz ripple off the full-wave bridge. When the ground and neutral are shorted together, this signal is sensed by a difference by the sense coil and again trips the switches to deactivate the circuit and isolate the fault. GFCIs of this generation can and do become weak, get sick, and die, especially when they've been in continuous service for decades. When they do, they often fail in the reset state, that is, with the circuit unable to turn off the current in the event of a fault. This means it's especially important that you test your older GFCIs to make sure they are still operating correctly. And if they aren't, replace them ASAP, or hire a licensed electrician to do it. If you found this video interesting, informative, or entertaining, please consider subscribing to my channel. And of course, I appreciate the feedback in comments or in likes. Thank you for watching.